Hi everyone, in this lecture we'll be talking about Earth's atmosphere. We'll talk about its structure, so that is how pressure and temperature and moisture is distributed from the Earth's surface up to the top of the atmosphere, the composition of the atmosphere in terms of the key atmospheric gases and the aerosols and their impact on energy, solar radiation, as well as how solar radiation drives land atmosphere interactions that we very briefly touched upon in the last lecture on solar radiation. The atmosphere, it's critical to life on Earth. If we didn't have the atmosphere, we wouldn't be around talking about how important it is. It contains the air we breathe. It retains all of our emissions, be they natural or human generated. It regulates the temperature of the Earth, protects us from the vacuum of space, the harmful radiation that comes from all sorts, the sun and etc. But it's the spatial temporal structure of the composition of the atmosphere that we're interested in, particularly as it relates to weather and climate and what we're studying in this course. So let's talk about the layers of the atmosphere. From the Earth's surface to about an altitude of 12 kilometers, we have the troposphere. Commercial airlines fly at about 10 kilometers. Over here we have the Himalayas. Mount Everest is about 8,000 or so kilometers above sea level. All life we know has lived in the troposphere. It's where weather happens. And it's pretty much where we'll concentrate our studies in this course. Above that, we have the stratosphere. Earth's surface to about 50 kilometers altitude. It's important. It has the ozone layer, which we'll talk about later. Some weather balloons can extend up to about 30 kilometers into the atmosphere. So that's that. The mesosphere is above that, from 0 to 85 kilometers. The mesosphere is where anything coming from outer space starts to burn up. So that's where we'll see the start of meteor showers. And at the intersection of the mesosphere and the overlying atmosphere's thermosphere, we have the aurora between 100 and 300 kilometers altitude, the aurora borealis in the northern hemisphere, and the aurora australis in the southern hemisphere. And inside the thermosphere, we have the International Space Station orbiting at about 400 kilometers above Earth. The thermosphere extends up to about 700 kilometers in altitude. Above that, we have the exosphere, and that's where we will find our polar orbiting satellites. Anything above 700 kilometers is pretty much outer space. That's where my bread and butter, the satellites that we use to monitor the Earth system, are located. Just out of interest, the geostationary satellites that we'll talk about at some point over this course, they're about 30,000 kilometers away from the Earth. So much further distance than these polar orbiting satellites in the exosphere. So the troposphere is at lowest 12 kilometers or so of the atmosphere. It's where we live, it's where weather happens. It's characterized by strong vertical mixing. That means the molecules that make up the troposphere can circulate from top to bottom in the order of a few days. It has 80% of the mass of the atmosphere, but about 100% of the mass of water in the atmosphere is located within the troposphere. There's a decrease in pressure with altitude throughout the troposphere, and generally, temperature decreases with altitude in the troposphere. The stratosphere is the layer between 12 kilometers and 50 kilometers in altitude, with the troposphere that combines 99.9% of the mass of the atmosphere in the troposphere and stratosphere combined. As I said, that's where we find the ozone layer. It's a critical gas for shielding us from the harmful ultraviolet rays from the sun. It's characterized by weak vertical mixing. That's why when stuff like volcanic dust or nuclear explosions make it up to the stratosphere, it sticks around for a lot longer and can be transported vast distances. Residence times in the stratosphere from weeks to months to years for some things. Pressure will decrease with altitude throughout the stratosphere, but we'll find a general increase in temperature with altitude. That's because of that all-important ozone layer that absorbs all that UV light. Remember, energy in has to equal energy out. So that energy out comes in the form of heating up the stratosphere. The layer above the stratosphere is the mesosphere. It extends up to about 90 kilometers from the top of the stratosphere. It's where we find meteor showers and aurora. It's characterized with the bottom part of the so-called ionosphere. There is a decrease in pressure with altitude and a decrease in temperature with altitude through the mesosphere. At this point, you're above, at the 100 kilometer above the Earth's surface, you're pretty much on top of the atmosphere. Then you've got the thermosphere. It's where we find the International Space Station. It extends up to about a 700 kilometer altitude above the Earth's surface. Here we see temperatures greatly increase up to 2000 degrees Kelvin. It's hard. It's not the kind of temperature we expect. Say being on Earth, the heating of the air around us gives us what we sense as temperature. Rather, this is the direct input of solar radiation into anything that's up there can raise the temperature up to 2000 Kelvin or so. Then above the thermosphere is the exosphere. It's where my beautiful Earth-observing satellites are located, and it's pretty much outer space. So that vertical structure of the atmosphere is characterized by temperature and pressure. So here we have those layers. From the Earth's surface, we have the troposphere, stratosphere, stratosphere, mesosphere, and thermosphere. Here it's showing that on the right-hand side y-axis, as you go from the surface up to the top of the mesosphere, or into the thermosphere, you have that decrease in pressure that's pretty much constant throughout the whole atmosphere. Temperature, this red line, on the other hand, has a very different behavior. As generally, we'll see what I mean by generally later, but the troposphere, we get a decrease in temperature up to about 10 kilometers. Then there is a pause in the rate of change of temperature, this so-called tropopause, where the temperature doesn't change much with altitude. Then, because of that absorption of ozone in the stratosphere, there is that increase in temperature through the stratosphere until we get to the stratopause. Again, there's regions of no change in temperature with increasing altitude with the stratopause. Then we have the mesosphere, where temperature decreases again up to the 85 or so kilometer mark above Earth's surface. And we have the mesopause, and up to the thermosphere, where temperature increases up to those 2000 plus Kelvin values. So we have those pause layers, the tropopause, stratopause, and mesopause, as the temperature stays constant with increasing altitude. So what gives rise to the vertical structure? Well, there's two main forces at play. We have gravity on the one hand, and then we have buoyancy force. Gravity, as you recall, is the force of attraction between two masses. It's inversely proportional to the distance squared between the two masses. Now, Newton's great contribution was to demonstrate that what we feel as gravity really is the force of attraction between us and the Earth. We get the force of gravity acting on an object is its object's mass times the gravitational constant. Now we'll say gravitational constant G, so it's 9.8 meters per second at the Earth's surface, but because of this R squared relationship, this force of acceleration due to gravity, G, this acceleration due to gravity, G, changes as we move away from the Earth's surface. So you could, in principle, as an exercise, determine what G would be if we're at the top of the mesosphere layer of the atmosphere, about 100 kilometer altitude. Maybe that's a tutorial question for later. So gravity on the one hand, being that attractive force, bringing the constituents of the atmosphere, pulling towards the Earth's surface. So why doesn't it all just collapse? Well, that's because the atmosphere has an opposing force to gravity that's a function of the density of the atmosphere. Now, the atmosphere is a fluid overlying the Earth's surface, and it's characterized by density rho f. And so we can have the opposing force to gravity as buoyancy, density times the volume displaced by that object and the acceleration due to gravity. When the buoyancy is less than the force of attraction due to gravity, an object will sink. Gravity takes over and wins. However, when the buoyancy force is equal to the force of attraction due to gravity, that's where we have those two things equaling. And you might know about Archimedes jumping out of a bath because he understood how it can determine the density of a material from the volume of water it displaced. And so this is where we've got an equilibrium and things will float. Oops. Oh, and the final thing is when buoyancy is greater than the force of due to gravity, the object will rise. The question might be, why will buoyancy be greater than the force of attraction due to gravity? And this will be a function of the density of the fluid. So what drives density? Keep that in mind. Okay, so on the left, we have force of attraction due to gravity pulling down on the air mass. The air mass has a force that it exerts on the Earth's surface. The surface we can characterize an area. So force over area gives us our units of pressure, Pascal. Buoyancy force, this is just a nice illustration how it's a function of density. So less dense things will float above more dense things. The less dense fluid, it will float above a more dense fluid. How we measure the temperature, pressure, humidity variations in the atmosphere one way is through the radiosondes. And I'll pause at this point and resume in a few minutes.